Today, we're going to take a look at finite state morphology, specifically looking at flag diacritics. If you'd like to follow along, we are going through content from the textbook Finite State Morphology by Kenneth Beasley and Laurie Cartoonen. Specifically, this material will be covering material from 7.3, Chapter 7, Section 3. To motivate this example, we're going to use an artificial language. Here is a small sample from that language. In this example, we can see various inflections of a single verb, the verb to eat. This example shows several verb moods and tenses. We want to build a finite state model that encompasses all of these, but does not allow incorrect forms. In this language, the root is specified in the center of the word. In this case, a simple root, just the letter B. The inflection takes the form of a circumfix, specifying mood and tense, sometimes implicitly aspect. The simplest form is the infinitive, marked by the circumfix I. A circumfix has a beginning and an end, with a stem going in the middle. In this case, the circumfix is I. Another way of viewing this is that if a word begins in I, it must also end in I. Over here, we have a rough gloss, to eat. Let's look at the indicative. So the indicative, past, present, and future, encompasses meanings such as they ate, they are eating, or they will eat. If a word begins in U, it may end in O, meaning past indicative, I, meaning present indicative, or U, meaning future indicative. The imperative specifies commands, such as eat, meaning right now, or eat, meaning at some point in the future, eat. If a word begins in A, it may end in A, specifying the present imperative, or it may end in U, specifying the future imperative. The interrogative mood is used for questions, such as did they eat, are they eating now, and will they eat in the future. If a word begins in E, it may end in O, specifying the past tense, I, specifying present tense, or E, specifying future. And finally, we have the subordinative mood, used for such meanings as having eaten or being currently eating. If a word begins in O, it may end in O for the past tense, or I for the present tense. So, with this in mind, let's begin our finite state model. We will be using the Finite State Morphology Toolkit, FOMA, although most of what we're doing could be used in other toolkits as well. Let's build a simple finite state machine that allows more than what we're looking for. In this model, a word can begin with any vowel and end with any vowel. Has one B in the middle, and has one vowel at the end. This is the corresponding finite state machine. Starting from state 0, one vowel, one B, one vowel. If we list the words accepted by this machine, we see that a word can begin and end with any vowel. Let's break this up into components. A start, a middle, and an end. We will then construct a regular expression composed by concatenating start, middle, and end. And we have the same machine that we started with. The next step is to start putting restrictions. These restrictions will come in the form of flag diacritics. In FOMA, a flag diacritic takes the following form. A flag diacritic is a special multi-character symbol that begins and ends with an @ sign, after the first @ sign is an operator, which will be a single letter, followed by a period, followed by a feature, followed by a period, followed by a value, and the final @ sign. The operator can take the value of capital P for positive setting of a feature, capital N for negative setting of a feature, capital R to require a feature, capital D to disallow a feature, capital C to clear a feature, or capital U to unify a feature. Feature is a user-specified string and can be any alphabetic string. Value is likewise user-specified and can be any alphabetic string. Let's use the P operator to positively set a feature, and we'll name the feature vowel. We could set any value for the vowel, such as hello, but that's not terribly meaningful. So instead, we'll set the value to A. Let's look at the resulting machine. The resulting machine will have one string, the letter A. When the finite state toolkit, FOMA, traverses this arc, it will treat this value, this special multi-character symbol that is a flag diacritic, as having special meaning. Specifically, FOMA will use the operator to determine which operation to perform, in this case, setting a value unconditionally. The feature to set will be vowel, and the value will be A. We see here that the string A is the word in the language, but the flag diacritic does not occur. Let's continue. In our language, we want a word to be able to start with A, E, I, O, or U, with certain restrictions. This machine has 5 words encoded in it. Notice again, the flag diacritic does not get printed out as part of any word. Going along this path, resulting in the word A, the flag diacritic causes the feature vowel to be set with the value A. But along this path, the feature is not set. Let's give this a name. We'll keep middle defined as B, and we'll define end with a restriction. The restriction that we're going to put in is a require restriction. So in order for the word to end in A, we're going to require that the vowel feature have a value A. For now, we will leave the others with no requirements. Let's take a look at the resulting machine. If we traverse from state 0 to state 1, then the only way to continue is by setting the vowel feature to A. We then continue to state 3, and if we want to continue on to have a at the end of the word, we can only do so if the vowel feature already is set to a, which it will be if we traversed that path from 1 to 2 to 3 previously. However, if we had previously traversed from 0 to 2 to 3, we will not be allowed to traverse from 3 to 4 and on to 5. Let's verify this. Notice that when we list the words from this machine, the only word that ends in a also begins in a. Let's add another flag diacritic. This time for the letter E. For the letter E, we will set the value of vowel to E. And in end, we will likewise require that the vowel feature be set to E. When we look at the machine, we now see that the path involving a word beginning with E will set the vowel flag to a value E. The path at the end of the word involving E will require that the vowel value be set to E. In this way, if a word begins with E, it can end with E. If a word begins with A, it can end with A. But if a word begins with anything other than E, it will not be allowed to end in E. If it begins with anything other than A, it will not be allowed to end in A. We can confirm this by looking at the list of words. The only word that ends in E also began in E. The only word that ends in A also began with A. Let's keep going. We will positively set the vowel feature to value I. Next, let's add a flag diacritic to the suffix I. Here we're going to use an operator that we haven't used yet, the disallow test. The abbreviation for disallow is D. Here, we are going to disallow the vowel feature to have a value of I. This is very different from what we did before, where we required the vowel feature to have a specific value. Here, we are saying the vowel feature must have any value except I. Now, when we look at the machine, we could walk through it again. If the word begins with I, it will set the vowel feature to I. Later on, at the end of the word, in order for the word to end in I, the vowel feature must be set to something other than I. Let's take a look. When we list the words, we see that we have ABI, EBI, OBI, UBI, but not IBI. Let's keep going. For the beginning of the word, if we have O, we're going to use one other operator that we haven't seen yet, the N operator, to negatively set a feature. The feature will still be the vowel feature. And here we're going to set A. The way to interpret this is as a negation of the value A, or specifically the complement of value A. What this means is that at this point, we are setting the vowel feature to be essentially anything other than A. And this is where the machine currently stands. Let's keep going. Next, we're going to use the unify operator. The arc from state 6 to state 7 now has a unification operation. If the vowel feature has not been set at this point, it'll be set to E. If it already has a value of E, that's fine. If it has a value of something else, it will not work. So let's look to see which words end in O. OBO, EBO, and UBO. These are three different situations. EBO is the simplest. The value of feature vowel was already set to E. It matched in unification, and that's allowed. In this case, with U, the vowel feature was unset, and so the unification operator set it. In the case of O, the vowel feature was set to be not A. At unification time, the value E is compatible with not A, and so is set to E. At this point, we're almost complete. Let's note that we could change one of these P values from the beginning to a U, and it'll effectively have the same result. In other words, if a value is previously unset, P in most circumstances will have the same effect as U. It's only when the values are already set that P and U will have very different semantics. P always succeeding, U succeeding only if unification is possible. Finally, let's add a flag diacritic for the U ending. Here, we're going to do a unify operation with the vowel A. In other words, we can only end in U if we began with A. Here is our final machine. This machine will produce exactly the set of words that we're looking for. ABA, ABU, oh, looks like I made a mistake, ABI. Let's take a look. We'll define start, end, middle, and finally, look at the words. ABA, ABU, EBO, EBI, EBE, IBI, OBO, OBI, UBO, UBI, and UBU. This example uses various flag diacritics. We didn't use the clear feature, but we used the others.